Thank you. Thank you very much for the invitation to speak here, and thanks to everyone for sticking around until the bitter end. And since I am the last speaker, I think I should also thank the organizers one more time for just putting on a terrific conference. This is my first time presenting at an AlCoVE conference, but I've enjoyed them since the beginning. And now we are going back to conferences in person, but I think there still is a place for online conferences as long as you do them the right way. And AlCoVE really shows you how to do the online conference the right way. Okay, yeah, so I am going to be talking about a certain class of partially ordered sets, posets. And these posets are going to be graded. So let me remind you what that means. Okay, so a finite poset P is graded of rank n if, roughly speaking, we can break the poset into ranks so that all of the cover relations are between adjacent ranks. So the formal definition is written there, but maybe this picture makes it clear what is going on. So here we have one element at rank 0, two elements at rank 1, and one element at rank 2. And so whenever we have a finite graded poset, we can form the rank generating polynomial of the poset, which just is the generating function for the number of elements at each rank. So this poset, 4-element poset, has rank generating function 1 plus 2x plus x squared, which is also 1 plus x squared. Yeah, so the reason we like graded posets is because we can extract sequences of numbers or generating functions out of them. And not just the rank generating polynomial, but another important polynomial associated to a finite graded poset is its characteristic polynomial, which is almost the same thing as the rank generating polynomial. We sum over all elements P in our poset, x to the rank of that element P, but we weight it by this Mobius function evaluation from the minimum element 0 hat to our given element P. And for the experts, you might notice that this definition of characteristic polynomial is slightly different from what you're used to probably. This is like the reciprocal polynomial of the usual definition. You'll see why I do that in a moment, hopefully. Okay, but so in this definition of characteristic polynomial, I have used the Mobius function. Again, hopefully most of us have seen Mobius functions before, but let me remind you of what the Mobius function of a poset is. So probably the quickest way to define the Mobius function, although not necessarily the most enlightening, is recursively like this. So for any elements x less than or equal to y, we define the Mobius function value mu xy to be 1 in the case when x equals y. So mu of xx is always 1. And if x is strictly less than y, then mu of xy is defined recursively in terms of smaller Mobius function values. So the point is that we want, when you sum below any element, to get 0, basically. So, I mean, this picture here is depicting how we would compute the Mobius function from the minimum 0 to each element in the poset. We start at the bottom, and the Mobius function value is 1 at the minimum. Then for the atoms, the things covering the minimum, they have Mobius function -1 to sort of balance out the 1 coming from the minimum. And then for that maximum element, it has Mobius function value +1, so that the sum of everything we see is 0. Okay, and so then the characteristic polynomial of this poset is 1 minus 2x plus x squared. That's keeping track of the Mobius function values at each rank, which we can also write as 1 minus x squared. Again, I said the Mobius function has many guises. So it has topological significance as an Euler characteristic. It has algebraic significance in terms of the incidence algebra of the poset. And probably like most important from the combinatorial point of view is Mobius inversion, which is a generalization of the principle of inclusion-exclusion to any finite poset or locally finite poset. Okay, so that hopefully is some pretty standard stuff. I want to, oh yeah, let me do some examples. So some important finite posets for me will be the Boolean lattice, Bn of subsets of the numbers 1 up to n. And we sort of saw this example already, B2 the rank generating polynomial, the coefficients are the binomial coefficients, and that's 1 plus x to the n. The characteristic polynomial is 1 minus x to the n, and it has almost the same coefficients, but they have this negative 1 to the k sign. Another very well-known family of finite graded posets are the partition lattices pi n, which are the lattices of set partitions of the numbers 1 up to n under refinement. So this is the partition lattice pi 3. And it's well known that the coefficients of the rank and characteristic polynomials for the partition lattices are the Stirling numbers of the second and first kind. And that means that the characteristic polynomial of the partition lattice factorizes in a very nice way, as shown here. So again, these are standard examples. So the posets that I'm interested in are actually infinite posets. So I want to do something similar now for some infinite posets, which are modeled on the natural numbers. So we say that an infinite poset is n graded, where here n is the natural numbers n, if we can, again, sort of break it into ranks so that the cover relations are between adjacent ranks. And we can define the rank generating function of finite type n-graded poset to be, well, exactly what we think it is. It's just telling us how many things are at each rank. So here, finite type is just the assumption that each rank has only finitely many things in it, so that this sum really makes sense as a formal power series. And similarly, we can define the characteristic generating function, again, assuming that our poset has a minimum, to be the same thing, where we weight each x to the rank of p by the Mobius function value mu from the minimum to p. Okay, so let me show you a couple of examples of finite type n-graded posets and their rank and characteristic generating functions. So one example is just the natural numbers squared, so this kind of grid poset. Its rank generating function is sum n greater than or equal to 0, n plus 1 times x to the n. So there's n plus 1 things at rank n. And that can also be written as 1 over 1 minus x squared, a rational function. And what is the characteristic generating function? Well, I'm showing you with those red circles computing the Mobius function values. And we see that they sort of all become 0 after a certain point. So it's, even though it's a priori a formal power series, it's actually just a polynomial. 1 minus 2x plus x squared, which we saw before, is 1 minus x squared. A different example of finite type n-graded poset, which might also be very familiar, is Young's lattice of integer partitions. Of course, the rank generating function of this Young's lattice has as its coefficients the partition numbers, which can also be written as a product. But again, we see that the Mobius function values become 0 after a certain point, so the characteristic generating function is very boring, just 1 minus x. Okay, so any questions about that? Again, please stop me if you have questions, or type them in chat. I can see the chat. So these are the kind of structures I'm going to look at, but you might notice there's sort of a difference between Young's lattice and the grid n squared, and kind of understanding that difference is something I'm going to be interested in. All right, so now we come to the main definition of the talk, Upho-ness. So we say that an infinite poset P is upper homogeneous or Upho if, for every element P in our poset, the principal order filter generated by that element P, which just means everything above that element, is isomorphic to the original poset. In other words, when we look up from each element, we see another copy of what we saw before. And I really should have put this on the slide. I mentioned it in the abstract, but this definition is not due to me. This is so this class of posets was introduced a couple of years ago by Richard Stanley, and he also came up with this name, Upho, which is very nice. So I like that a lot. Okay, so that's a cartoon picture of what an Upho poset looks like. But let's see some examples. So first of all, okay, the natural numbers have this property, just with their usual total order. We look up from any natural number, we see sort of the same infinite chain. Same thing with the non-negative rational numbers, the non-negative real numbers. An example that's not a total order would be the finite subsets of any infinite set ordered by inclusion. Okay, but all of these examples are a little bit, well, all of them except for the first one, the natural numbers, are a little bit too infinite for me. Yes, Young's lattice, that's a good observation, Maria, is not upper homogeneous. So maybe that's already hinting at what the distinction that I wanted to draw was. Okay, so I'm going to restrict to finite type n-graded posets so that I can form the generating functions that I talked about. So the only example in this list that's finite type n-graded is just the natural numbers n themselves. A quick observation is that the product of two upper homogeneous posets is still Upho. So n to the n is Upho for any n greater than or equal to 1. So for example, the grid here is a good example of an upper homogeneous poset, n squared. Let's see some more examples of Upho posets. So here's one on the left, the binary tree poset. So, you know, it's just an infinite binary tree rooted at the minimum element 0. The number of things at each rank is 2 to the n, so the rank generating function is 1 over 1 minus 2x. And you can compute that the characteristic generating function is 1 minus 2x. Again, just a polynomial, not a formal power series. Here's a different example. This is what I call the necktie poset, although it also sort of looks like bow ties. So I think it was previously called the bow tie poset. Sort of depends on your perspective. You can try to, it's like one of those images where it looks like a rabbit or like, anyways. Okay, so this poset just has two things at every rank starting at rank 1 and all of the cover relations between them and then a minimum element at rank 0. And you can work out what the rank and characteristic generating functions are. So they're written there. The rank generating function is 1 plus x over 1 minus x. And the characteristic generating function is 1 minus x over 1 plus x. And we finally see an example where the characteristic generating function is actually a formal power series. It seems that f and chi are always reciprocals of each other. And your example is very good observation, Sergey. So this would be the point in the talk where I asked to guess the theorem based on the examples. And I think it's been guessed. One more small observation before we state the theorem that Sergey alludes to is these examples have two atoms. So an atom is something which covers the minimum, so something at rank 1. And they have obvious generalizations to any number of atoms. Just like with n squared, I could do n to the 3 or n to the 4 and so on. So we can have examples with many atoms, but these are just sort of the easiest to draw. Okay, so here we come to the theorem, which is that for any upper homogeneous poset P, the rank generating function is the reciprocal, the multiplicative inverse of the characteristic generating function. So this is a very nice result, but it's not like a deep theorem. So it's extremely risky to like present a proof at a talk, especially one that's as short as this. So I don't think I will present the proof here, but I have it written down just to show you that it's something you can do in one line from Mobius inversion. So it's just really a simple fact, but once you see it, it's very nice. And yeah, so you can stare at that if you want. But let me just say, yeah, so this is a nice result, but it's easy to prove from sort of any definition of the Mobius function that you start with. Mike asks about the converse. The converse is definitely false because yeah, I mean, just the generating functions don't tell you enough about the structure of the poset to recover it. Okay, but here's, so I guess I didn't really state what my goal or objective was. So we have this interesting symmetry structure, and we just want to understand, like, what do Upho posets look like? Like, can we classify them, for example? That would be amazing if we could classify Upho posets. Unfortunately, this group of 4 authors, which I think was a result of like an MIT Primes or Spur, one of those sort of research projects that I think was led by Yibo Gao. So what they showed, they actually proved a lot of nice stuff about Upho posets. And one thing that they showed was that there are uncountably many different rank generating functions of Upho posets. And so I think this answers a question that just appeared in the chat. So since there are uncountably many rank generating functions of Upho posets, there have to be ones which aren't rational. In fact, they're sort of uncomputably bad. Okay, so that sort of dashes our hopes for classifying Upho Posets in general. But here's something which is really nice, which is when we restrict to a lattice, things change. So again, a lattice means that we have joins and meets, least upper bounds and greatest lower bounds. And if I'm given an Upho lattice, I can consider the following: the interval from the minimum 0 to the join of the atoms. So if I have R atoms, S1 through SR, their join exists in this lattice, and I can look at the interval from the minimum to that point, and I'm going to call that interval the core of my Upho lattice. And it's a simple corollary due to Rota's crosscut theorem that there cannot be any non-zero Mobius function values above the core of the Upho lattice, which means that because of this theorem, if I have an Upho lattice, okay, so I denote all of my infinite posets by script letters. So the Upho lattice here is script L, and the finite things are denoted by normal script letters L. So the calligraphic ones are infinite, and the normal font ones are finite. Okay, so the rank generating function of an Upho lattice is the reciprocal of the characteristic polynomial of the core, which is a finite graded lattice. And so it's the reciprocal of a polynomial with integer coefficients. So in particular, that means there are only countably many rank generating functions of Upho lattices. So the situation is quite different when we restrict to lattices. We only get countably many different rank generating functions. This doesn't necessarily mean that there are only countably many Upho lattices altogether, although I suspect there probably are. That's sort of like an open question, actually. Okay, but so now we've clarified that maybe Upho lattices are the right thing to study because they're sort of more finite, and there are only countably many rank generating functions, and it also identifies the core as an important structure which governs a lot of the behavior of the Upho lattice. So I should say as a disclaimer right away that the core does not determine the Upho lattice in the sense that there can be multiple Upho lattices which have isomorphic cores. But nevertheless, if we wanted to classify Upho lattices, then we have to start with an answer to the question of which finite graded lattices are cores of Upho lattices. Is every finite graded lattice a core of an Upho lattice? So for example, we saw that the Boolean lattice, B sub n, is the core of the natural numbers n to the n. So the Boolean lattices are cores. Okay. And I don't have anything like a complete solution to this problem, this question, but I'll give you some positive and some negative examples that show that it's very subtle. And as I wrote here on the slide, one way to think of this problem is it's sort of like a tiling problem. We have some finite lattice, which is our tile, and we're trying to sort of position many copies of it together to produce an infinite lattice, which is sort of fractal in nature, right? Okay, so this is the question I want to focus on: which finite graded lattices are cores of Upho lattices? I'm going to present, as I said, both positive and negative results. Okay, so that's spoiling the fact that not all lattices are. But let's start with the positive results. So I mentioned that the Upho lattice is not determined by its core, and here's an example showing that. So let me fix any positive integer k greater than or equal to 1, and consider the finite subsets of the positive numbers, 1, 2, 3, and so on, which have the property that the maximum element of that subset is at most k plus the size of the subset, or sorry, the maximum is strictly less than k plus the size of the subset. So this is an example with k equals 2. For example, 1, 3 is allowed because the max here is 3, and that's strictly less than 2, the size plus 2, which is k. Okay, so 1, 3 is in this collection, and we order this collection just by inclusion. What you'll notice is that or you can sort of see in this example, so this is an upper homogeneous lattice, and its core is, I mean, in this example, it's B2, and in general, the core is the Boolean lattice B sub k. But it's not isomorphic to the natural numbers to the kth power. So this is sort of the simplest example showing two different Upho lattices with the same core. You can see that sort of just because, like in this example, there's something which covers 3 elements, and that can't happen in n squared. So, okay, so this is just a different way of realizing Boolean lattices as cores. But what we're actually interested in is like sort of which things arise as cores. So let me show you another construction that's similar. So again, we're going to fix a parameter k greater than or equal to 1, and we're going to look at the collection of set partitions of a set of the form 1 up to n for n, any number greater than or equal to k, into k blocks. And we're going to order these by refinement. So for example, when k is 2, I'm looking at partitions into 2 blocks of sets of the form 1 up to n, where n can vary, and n can be anything greater than or equal to 2. So for example, 1, 4, comma, 2, 3, that's one partition of 1 up to 4 into 2 blocks. And so that's something in this collection. And I'm still ordering these by refinement in the sense that one set partition is less than another if all of its blocks are subsets of all of the blocks in the other partition. And what we can show is that this is an Upho lattice whose core is actually the partition lattice pi k plus 1. And if you think about that, it implies kind of an interesting fact about the Stirling numbers, because the characteristic, or sorry, the rank generating function of this Upho lattice is given by the Stirling numbers of the second kind, but that's supposed to be sort of the reciprocal of the characteristic polynomial of the partition lattice, which has the Stirling numbers of the first kind as its coefficients. So it's an interesting duality between the two Stirling numbers. And so these two examples, which realize the Boolean lattices and the partition lattices, they can be generalized to what are called a uniform sequence of supersolvable geometric lattices. So this is going to be a sequence L0, L1, L2, et cetera, of finite graded lattices where Ln has rank n. And I don't want to define what these terms mean, but just think about they're a sequence of graded lattices that are embedded in one another in a nice way. So these were studied by Stanley and by Dowling in the 70s. And if we sort of combine their work together, one thing we can show is that, the notion of a uniform sequence of lattices is due to Dowling. The notion of a supersolvable lattice is due to Stanley. And combining them together, we can give a nice formula for the characteristic polynomial of any of the members of a uniform sequence of supersolvable geometric lattices. And using sort of similar ideas, we can show that for any member LK of a uniform sequence of supersolvable geometric lattices, there is some Upho lattice which has that as its core. Okay, so the consequences of this are that many families of well-studied finite graded lattices can be realized as cores. So for example, the Q analogs of the Boolean lattices, the subspace lattices, the type B Coxeter arrangements, Dowling lattices. Okay, these can all be realized. I might skip over this example just because of time considerations, but there's another way of constructing Upho lattices which involves monoids. So if you like monoids, then you can also study Upho lattices from that perspective. And let me just say that using some known facts about monoids and some Coxeter group theory, we can show that, for example, the weak order and the non-crossing partition lattice of any finite Coxeter group are also cores of certain upper homogeneous lattices. Okay, I want to get around, though, to showing some negative examples as well. So how can we show that a finite graded lattice cannot arise as a core? Well, one thing to notice is that the reciprocal of the characteristic polynomial is supposed to be the rank generating function of our Upho lattice. So if the reciprocal of our characteristic polynomial has negative terms in it, then definitely that cannot be a generating function of anything. So that's a simple way to show that you cannot be a core if you have negative terms in the reciprocal of your characteristic polynomial. And there are other obstructions too that are more sort of structural in nature, but again, let me sort of skip over that because it's a little technical. So let me just show you some examples. If we consider the octahedron and its face lattice, then you just type into Sage and it will tell you that the characteristic polynomial of the face lattice of the octahedron is this thing, 1 minus 6x plus 12x squared minus 8x cubed plus x to the 4. And if we take the inverse of that as a formal power series and look at the coefficient of x to the 13, well, that's a negative number, which means that the face lattice of the octahedron is not the core of any Upho lattice. Similarly, the face lattices of the n-dimensional cross polytopes and n-dimensional hypercubes are never cores when n is greater than or equal to 3. Another example are bond lattices of graphs. If we type the cycle graph on 4 vertices, well, its characteristic polynomial, that's almost the same thing as its chromatic polynomial, is given by this, and the coefficient of x to the 7 in the reciprocal of the characteristic polynomial of the bond lattice of the cycle graph on 4 vertices is negative 80, which means that that bond lattice is not a core. And you can show in a similar way that cycle graphs, their bond lattices, are never cores for n greater than or equal to 4. A nice question is which graphs have bond lattices that are cores. It could be, for example, the supersolvable bond lattices, which were classified as by Stanley as being the chordal graphs. Okay. Yeah, so let me just mention very briefly some future directions. So far what I've talked about is just whether a finite graded lattice can be realized as a core. And a natural question is, well, let's fix a lattice which can be realized as a core. In how many different ways can it be realized as a core? And that's something that we're looking at in joint work in progress with Joel Lewis. Some things that we can show are this number is finite as long as L has no non-trivial automorphisms, which suggests it might be finite for all L, because that's a weird condition that doesn't seem related at all to this Upho-ness business. On the other hand, we can show that even restricting to rank 2 lattices, as the number of atoms goes off to infinity, the number of ways to realize that rank 2 lattice as an Upho lattice, as the core of an Upho lattice goes to infinity. So there's no sort of bound on this number. So they can be realized in many, many different ways, but potentially only finitely many ways. And the last thing I want to mention is that you might want to restrict to certain classes of lattices. So for example, distributive and modular lattices are important subfamilies of lattices. So it's not hard to show that the only distributive Upho lattices are n to the n. But the modular Upho lattices are much more interesting. So here's an example. If we fix a prime p and any positive integer n greater than or equal to 1, then the subgroups of z to the n of index a power of p gives a modular lattice by reverse inclusion. So this was observed by Stanley, and he sort of conjectured more generally that every modular Upho lattice comes from, well, you could call it commutative algebra, or you could also say this is basically an affine building. So basically affine building should be all the modular Upho lattices. And that's an interesting open conjecture. Okay, so let me stop here. Thank you.
Hey, thank you, Sam. I was so wrapped up in the math that I almost forgot that I'm supposed to be like hosting here. So there's a lot of questions in the chat here. So why don't we start with them? There's a question Nikita Borisov asks, is there a connection to Milne's theorem, which generalizes the reciprocal duality of Stirling numbers of the first and second kind?
Yeah, so I think this was in the context of these like super solvable uniform sequences of super solvable geometric lattices. And all I can say, Milne or Milner? I'm feeling like maybe Milner was meant. I don't know. But yeah, I don't know anything about that, except that it sounds very similar to something that Vic Reiner told to me once, which so you probably could ask Vic about that. I see another question about real rootedness of characteristic polynomials, and again, I don't know the this is something that I think Yibo Gao and his students have looked at, is kind of the positivity properties of these rank generating functions. So you could probably look in those papers. I don't know the exact details, but I do know that they looked at like real rootedness and sort of sure positivity and positivity in general. So I think that that has been investigated to some degree.
Okay, let's open up to like audio questions. If anybody else has other questions here.
Can I ask a random question? So I think could you go to the slide with like count the number of ways to realize a core?
Yeah.
Yeah, I mean, okay, maybe I was just confused, but yeah, so when I first saw your question before the actual like work that was done afterwards, I was just wondering if you had like anything on like uh yes, this K of capital K of L is like unbounded, but do you have any idea of like how like sizes are distributed in some sense?
Okay, so let's focus on rank two. Even so, rank two lattices look very boring, right? They have a minimum, a
Uh-huh.
maximum, some atoms, and so maybe they have that. I think usually Mn is denoting like when you have n atoms.
Uh-huh.
So we know that kappa of Mn is at least the partition number Pn. In fact, we can write down a monoid, which, for each partition, we can write down a monoid, which gives us a different lattice of that. And okay, here's something which is kind of like a conjecture. I don't want to call it conjecture, but a question. I don't know any examples which don't come from monoids. So every example that
Mm,
I've cooked up, I can figure out a monoid which realizes it. So it's possible that they
okay,
all are monoids. That would be kind of interesting.
I see.
And that's related to how we show the finiteness property. We show that if you don't have any automorphisms, then you have to come from a monoid, and there can only be finitely many ways for like sort of finitely many different monoids for a given core. So
Mm, I see.
I have a
Thanks.
question.
yeah, Maria.
So you mentioned that, there's uncountably infinitely many of these Upho non-lattices, just posets, and that's why some of them have non-rational generating functions. So that's sort of an existence proof. But do you have an explicit construction of an Upho poset that doesn't have a rational generating function for these series? Like, I'm
Uh,
curious what one looks like. Like, how do you construct a really bad Upho poset?
the it's not due to me. It's due to that group of
Oh,
four.
maybe I missed it. Did you say this?
I can tell you the answer is just it's the stuff that I didn't really talk about, which is this idea of monoids. So if you write down a monoid that has the correct properties of being left cancellative
Mm-hmm.
and yeah, they have a very explicit construction of uncountably many different lattices from, I mean, sorry, not lattices, but Upho posets, which are not lattices, but come from monoids. And since there are uncountably many the different rank generating functions of those ones. Yeah.
Right, but I mean, is there like a specific monoid that doesn't have
Oh,
a rational rank generating function that you can like write down?
uh, they do have ones written down, and it's just a parameter. Yeah, so I don't have a good example off the top of my head, and it is a little bit hard to draw pictures of,
Yeah, no, of course, because these are
but I
very
don't think it's too hard to come up with something